So I'm Krishna from NeuroBlade. What we do is build a hardware accelerator for analytics. And physicality is still important, so it is a real product that you can come up and take a look at after the talk. We're a company that was founded in 2018 with offices here and in Tel Aviv. I'm going to talk a little bit about the last line there, DAXL API for simple integration. DAXL stands for Data Analytics Acceleration. And the reason we talk about DAXL in the same breath as we talk about the physical product is what we're building is a general language for acceleration. It's a language that fits well in the open source world and integrates into the open source world. And we'll give you a little bit of exposure of what it is as we go through the talk. But why do we exist as a company? So we went all the way back in time to 2002 and looked at TPCH results and looking at the hardware that we got the results from. And you see this nice, roughly linear line. Performance, price performance kept improving with every generation of processor. We've all struggled with Moore's law. This is indicative of the same. It doesn't seem to apply anymore. We don't get better price performance with every generation. It's roughly flattened. And you see that in terms of what's now being done with CPUs and accelerators being embedded in the CPU for very specific things. But when it comes to something as big and as broad as TPCH, it's not something that we can just add as an adjunct to your CPU. We also see attempts at doing this with GPUs. But if you're not focused on this problem, the complexity of this problem, then the results aren't as outstanding either. How many of you know SQL? Come on, everyone, raise your hand. I know. It's a very simple query just to make a point as we walk through the slides. We need a base frame of reference. Now, I just jumped directly to the DAG, somewhat resembling a physical plan. It's in a very simple query where we select column A from table Y and filter on column Z. The DAG is scan table Y, then you do the filter, then you do the projection. Now, when we go look at a modern CPU architecture, and for some folks, this diagram isn't deep enough, acknowledge that up front, but we talk about it as if we do a scan and then a filter and a project. And in some cases, that is a linear stream, but it's not always perfectly linear, because we do a great job in parallelizing execution on a CPU, breaking the table down, the data frames down, separating instructions on each of the nodes. But at the deepest level, if we just look at the scan and decompose that further, what are we doing? We're reading, we're decoding, then we're doing the scan, and ideally we're pushing the filter into the scan itself. But if we further decompose, how many instructions on a CPU are required for each of those operations? With the level of parallelism that a CPU can provide, you still end up doing very linear-looking things. Not only that, your interactions aren't limited to within the confines of the CPU. It's a CPU, it's storage, it's memory, it's disk. Now, the specifics change with every interaction, but that sequence roughly exists. For some operations, for example, a filter, it's a CPU and memory. When you're doing a read, it's going all the way to across the network to your remote disk. If some of you are using cache, it's coming up to the cache if the data happens to be cached. And so this itself is a bottleneck that you can't get around when writing an execution engine. You can try to optimize, you can try to reduce, but you're limited to the instruction set Intel gave you. Now, we also rely, in general, on the OS for caching. So if you're not using a specific package, we kind of pretend that caching isn't a thing. Right? It just happens to be in memory. Sometimes it's on disk. Sometimes it's not. The OS manages a page cache. It's transparent to us in software. And so now your latency, when you go to memory, itself can be highly variable. You have no idea whether this is a memory operation or this is going all the way to local disk. So when you add all of these up, this ends up being a significant source of latency. What we've built, you can think of it as a very, very wide instruction width processor. Our native operations are scan, they're filter, they're project. And so a scan is not just read from the disk, but it's also decompress, it's also decode. That's one operation. So all the backs and forths that you do with your memory subsystems don't exist. Now, in traditional architectures, when you have something sitting on the side as like an accelerator, like a GPU, memory is still there. You're reading from a disk, loading it into memory, then processing on the CPU or shunting it to your accelerator. We also bypass that entire process. We read directly from the drives or directly from your DRAM, directly into the processor. Now, being a very wide instruction set also gives us another advantage, and we leverage this from the CPU world. The concept of pipelining instructions is not something we invented, but because we do it on the super wide instruction, we can now overlap a scan with a filter with a project. And the latency of a project is entirely hidden. You just get the little bit on the tail end that you actually see the latency of. The rest is overlapping with the filter and overlapping even with the scan. So it's another area where you get significant acceleration when you look at end-to-end processing time. And the last point here is zero copy in memory. If we take the projection and then we hand it back to the query engine, but it happens to be in our memory format, what happens? Someone has to do yet another conversion. So we said, let's not do that. Let's integrate with the open source memory formats and have exactly zero copy. We hand you a pointer, please operate on the data. You already understand it's laid out the way you expect it to be. Now, how do we fit in this ecosystem? We're at PrestoCon, so we're going to talk about Presto. But it really doesn't matter to us. I started with, we're building a data acceleration API and a framework that's generic. And everyone at NeuroBlade firmly believes in that. Now, each engine has specific extensions, and we understand that, and there are edges where we do have to be somewhat custom. But by and large, we're common, and the design is common. And so we say, Presto, Spark, Lakehouse, or customer engine, bring your own. And we're talking to customers that are still building their own execution engines, or they're building their own query engines end to end. Now, everyone has the concept of a worker node, and some concept of a planner and a plugin framework. In the Presto context, that's Hive or Iceberg, but not limited to that. If we can add a small plugin that can translate between the query engine and Daxel, then these two things can communicate and work together. And so that's what we're doing with Velox. That's what we're doing with Presto and others. Now, you come to the physical server. We're peer to the CPU. We're not replacing the CPU. We're not better than the CPU. We're a peer to the CPU. There are some things the CPU still does amazingly well. But there's a lot of things that we can do better. And by being a peer and working in this ecosystem, we offload the things that we do particularly well. And we rely on the CPU to provide a complete system from an physical hardware execution perspective. So we take care of a chunk of the query. The rest of the query goes off to the CPU to be complete. The more we take off of the CPU, the better your performance is. But we all know how complex SQL is. We know the landscape of data types is seemingly endless. Where we didn't want to be in a position of is, here, have this accelerator. By the way, you now can't run queries X, Y, and Z because we don't support data types A, B, and C. That didn't make sense to us. Now, we kind of have somewhat throwaway at the bottom of the slide is your persistent storage layer. Yes, we all have to support it. There's absolutely nothing we do special to work with it. The access is already in your connectors. It's already in the query engine. It's there for completeness, but there's nothing we have to do to work with object store. So what do? We have two modes of operation. We read from DRAM, or we read from drives. Right? DRAM is DMA. From drives, we coined a term, direct file access. When we read from local NVMe drives, we saturate the PCIe bus. Can't do that with one drive. You need more than one. But if you do, we can saturate the bus and read at the maximum speed that your drives can feed us data. That's only relevant because we can also process the data and process the query at that exact same frequency. The processor, we call it the SPU, SQL Processing Unit, is designed and frequency locked with the bus. So we think in terms of generation of PCIe. And everything is sized to make sure we can actually process whatever we're getting at that rate. If we're reading from memory, again, we can read at that rate, assuming the data can be made available at that rate. Now, there are certain cases where it can be. There are many cases where it cannot be. And when it can't be, we're going to saturate the rate that it can be made available to us. Now, how that data comes to us is a source of variability and a source of variability in performance. But we can share the best that we can do. Whenever I talk to anyone, they ask, do you support my favorite data format or table format? Do you support my file format? And what's the memory for? What is the zero copy thing you keep talking about? So we support all the common open source data formats or table formats, ClickHouse, Iceberg, Delta Lake, Hoodie, Hive. To us, it's somewhat immaterial. There are a bunch of names on a slide, not because I don't know what they are, but because when you look at how they're actually implemented, how does that impact something that's accelerating? If it's Hive, as an example, it's an external database sitting somewhere else. It doesn't matter. If it's Iceberg, the metadata is on a file co-resident with the data file in the same directory. But it's being interpreted by the query engine, and I'm being told to go scan file X for some period, some part of the file. File formats, on the other hand, are very material. When you go and look at file formats and look at how they're executed, right, you read it, you deserialize it, convert it into a memory format, process in the memory format, send the results back. By the way, you probably have a shuffle somewhere, so now you're deserializing and serializing yet again for the network. What the SPU does, it reads it in the native format, it understands the native format. In hardware, it processes the query on the file format itself. And then at the output stage, it converts it to the memory layout, and then sends it back to the query engine. And on the memory layout, today we support two, arrow and block. Arrow, because it seemed like the right emerging standard. Block, because that's the thing that's supported in ClickHouse. For both of these, we're not limited. The SPU itself is programmable. And so if someone comes up with yet another file format or yet another layout, it's a small project to extend to enable that support in the SPU itself. By the way, I forgot to announce, please raise your hand and ask questions along the way. Otherwise, this becomes a very dry talk. So we always love to talk about performance. But what I realized was it doesn't matter what numbers I put here. I don't know if one number would be more believable than another, right? Whether it's 10 times faster, I put 30 times faster, I put 100 times faster, would you believe me anymore? But these are the numbers that we claim. This is marketing, so I have to have a number. But the only way for it to be believable is not because we have a benchmark number. All of us collectively know that benchmarks are very limited in terms of what they show, and entirely unreliable in terms of comparing performance with your actual data set and your actual query load that you put on an actual running system. And so your mileage will vary. The only way for you to see that is to actually do an integration and test it out. But if you want numbers, we have numbers. More interesting is actually the card itself is a very standard form factor. How many of you are friends with your server infrastructure team? 1, 2, 3? All right, relevant for you guys. When you go ask them, like, can I plug this into my server? And they say no, well, then you're accelerating exactly 0x. And so we put a lot of thought into what is the form factor that we plug in, and can we plug in? And so we took the most common format of a card, and that's what this is. It says, as long as you have a PCIe slot available in your server, this can plug in.
Say 16?
16, yes, Gen 4. Gen 4, full height, half length, single width. You don't need a GPU server. And as far as I know, no one uses GPU servers for analytics anyway. Now, in terms of the logical flow, and how do we plug in, and how do we get to these claims? Someone writes SQL, whether that's your dashboard, that's a human, whatever. Then we get into the actual query engine, and there's logical and physical planning. I also have nothing to do with that. Then we get stage and task scheduling. We optimize, we plan for the shuffle, we pipeline. I also have exactly nothing to do with that. Finally, we get to the actual execution, and we introduced a new concept called task planning. Here, what we need to do is segregate the part of the query that lands there into what we call the SPU part and the CPU part. As the names imply, the SPU part is the thing that the SPU can actually process, and the CPU part is the rest. Now, the way we do it, and you'll see the code in a second, is really simple. We don't ask you to understand the limitations of what we can do. We give you an API that says, give me the substrate of the query that you have. And we, as the providers of Daxel, can tell you what we can process and what we can't. And then finally, when it comes to task execution, ask us to execute, and we're happy to do it. Please give us our part, not the CPU part. So if I summarize and provide it in a different view, in the middle, you have the operator group that came into execution. You have the SPU group, the SPU part, and the CPU part. There's some very simple rules around these two parts. An SPU part can feed into a CPU part. An SPU part will never feed into another SPU part, because then it would just be the same group. But a CPU part, as today, can feed into another CPU part. Now, in terms of the input can be from 3 different things. It can be the output of another task, right? The output of another CPU part. This is typically coming across a shuffle. It can come from DRAM. You happen to have read data from remote storage. What we ask is just do a bitwise copy into memory. Don't try to interpret. Don't try to deserialize. Make it available to me. Or it can be from a local drive. If it's in a local drive, I can read it and access it directly. On the other side, once we finish what we're doing, we hand over and finish the CPU part, assuming it's more than 0. And then the output goes exactly where you expect it to go, like it does today. It's another task on the same worker, it's going to another worker of a shuffle, or we're done and you're sending it back to the client with results. When we thought about Daxel and we thought about how do we make this available, we looked at rough diagram of what a query engine looks like. And to some of you, this diagram will be familiar. We looked at the data source connector and said, what are the relevant places for us to intersect? And there were three. There's the metadata. In order to do the acceleration that we do, we need to understand the schema of the data set itself. We can't do it agnostic of that. And so the query engine has to give us some DDL and tell us this is what we're operating on. We need to plan. This is the task segregation, CPU part, SPU part. And then we need to execute. That's the easy part. So let's walk through what this looks like. We have to compute a plan. This has nothing to do with us. Right? In this case, in this example, in the source code, hello Daxel. Right? Our version of hello world. Inside that JSON is a substrate representation of the query we're walking through. Then we're going to segregate the operators. So in Daxel, you have a statement, a function called prepare. You give it the JSON plan that you just read into from this file, or was passed into the worker. And then we give you the two segregated parts, the SPU part, the CPU part. You don't need to know anything about our limitations. Another benefit, like every other company, we will iterate on our product and we will do more over time. Your integration is completely unimpacted, because this API understands the limitations as they evolve. The parts themselves and the composition will change. But the integration happened once, and that's good enough. Once we have the SPU part and the CPU part figured out, we send it back to the worker. Here are the two parts. And now it's on the worker to execute. So in execution, you need to create a handle. You guys are familiar with this. Please give us our part, the SPU part, and there's some configuration options. For simplicity, it's config options, but there is a couple, and we can go into details if you come and talk to me. And then do the execution. Now, I haven't told it what to execute yet, so it's just preparing us for execution. But you now need to say, what is it that you want to execute? And so here, you're going to add splits. And so literally pass a file, a starting point in the file, and an ending point in the file. Right? So this is the file, scan this much, and process the query on this much of the data. And then we're going to give you the data back in chunks. So get next row chunk. And keep doing it. Now, in a hello world program, we just output it to the screen. Presumably, you're not going to do that. And then finally, we're sending the results back. So you have the output, you have the chunk, do what you need to do with it. Now, when we do that, actually go back one consideration we think about a lot at NeuroBlade is, are we sending it fast enough? And are we sending it too fast? And the reason is, we understand that the CPU is a peer. And there are multiple CPU parts happening at the same time as we're executing the SPU parts. And in that context, sending at the right speed is like putting water through a pipe. Water goes in, water comes out, it's at the same flow rate. That's great. What happens if it doesn't? What if the pipe narrows because the CPU is busy on something else? Now we're suddenly sending it too fast for the system to process. And how do we do that in a way, how do we do that and process a query in a way that we can continue processing on other things until the CPU is ready to process on the single stream that we just talked about? And so do that by replicating what the CPU did, concurrency. So now suddenly we can process multiple queries and multiple parts all at the same time, but only send the feedback where it's relevant and the CPU is able to consume the results. And finally, when we're done, there are no more data files to be read, the worker tells us, there's no more, you're done. And then all of those parts that we sent as we streamed out, they were processed through the CPU part by the CPU. Either that's the most interesting hello world, or the most clear, or everyone's asleep. So I talked about numbers. This is the last time I'll mention numbers, only because I only have one more slide. But we're working with the Velox community, or we're starting to work and engage in more and more ways with the Velox community to show what we can do. Velox does about 3x performance over Presto. If I remember my numbers correctly, we're providing the next 10x boost. So that's how we get to 30x. Now we think about and we talk about seamless integration. And this is how. Now I didn't get into a lot more detail. Happy to do that offline. But the goal, again, is to not have you think about multiple things. Right? As much as we can streamline and simplify the integration, the easier it is for you to try it out. Pedro, if you're in the room, close your ears. But we quoted you on the slide. We have created Velox to unify software-based optimizations into a single engine that can be reused across multiple query engines, Presto, Spark, and beyond. And our long-term strategy for Velox is to provide that unified framework. And this is really at the heart of why we chose Velox as one of our early engines to integrate with. We didn't want to be pigeonholed into a single engine. And Velox's vision, to fit into Presto as the native worker, but then to go beyond into other engines. And we saw talks, for example, of integrating it with Elastic today. Motivated us to integrate with Velox because it provides portability for our solution. We integrate with Velox, we go where Velox goes. We also learned that not everyone thinks about Velox the same way, so we're doing it with another engine. And by doing it with more than one engine, it's also allowed us to round out our solution so that we're not limited to one. Because when you do a second, you learn there's so much more common and there's certain edges and you think about problems differently. And we're confident that we're not limited to 2. We can do 3 and 4, and the level of work required to get to 2 will be even less when we get to 3. You guys are familiar with this, hopefully. All we had to do was add Daxel and the SPU at the bottom. It's as simple as that. Last chance to ask questions. Any takers? None. 1, yes, thank you.
So for these cards, you guys can provide the cards itself, right? No additional other hardware required.
That's right. You get this card and the software to enable it, which is Daxel. That's all you need. Sorry?
How much does the card run?
Let's talk about it. How much value do you see is a more important question to ask first. You know, we don't talk about 25% improvement in performance. Our target is minimally 10. So if I can reduce your server footprint from 10 to 1, what do you think?
I was trying to wrap my head around if you could drop in. I was trying to wrap my head around the integration with your card. What are the changes that you have to make additional components to fully integrate?
Can you repeat the question with the mic for everyone?
So, oh, Jesus, loud. So I was trying to wrap my head around the integration of the ecosystem with your card. So, you know, when I was thinking of like integration, I think of like sidecar, Kubernetes, drop-in, easy use. You know, what are the how does an application or how does the stack integrate with your hardware?
So there's 2 parts. There's how do you deploy the software that's behind Daxel as the interface language, and that you can containerize as you would like. So it can be as part of the OS. It can be in a container and sit to the side. Both are perfectly viable ways to deploy it. Then there's a client library, which is the thing you actually compile into Velox or into your query engine. And then the way they communicate is gRPC. And ideally, that's local, but you're not limited to local. Sorry, was there another question? Maybe? No? Okay. Any other questions?
Can you connect more than one Velox in SR?
So can you repeat? So if you have a question, raise your hand, and you will get a mic. Otherwise, I'll make you ask the question twice.
Can you connect more than one deluxe cards in the same server?
Can you physically? It depends on if you have more than one port, right? More than one PCIe. But yes, of course.
And in that case, the CPU is a limitation? Is like, or the CPU can handle both cards at the same time or more than?
So it depends on the workload of the CPU. There are many cases where you can't even consume the full output of one card. Right? And that's not our limitation. It's a limitation of how much you can process on the CPU itself.
Okay.
Any other questions? Your card is dependent on the DRAM of the system, right? I mean, you have there's no onboard memory.
So there's no onboard memory. You have a very good eye.
Yes.
There is on-chip memory, though. We use high bandwidth memory on chip,
Sure.
Which we need for certain operations.
But that would be zero copy then, right? That's getting pushed back out to DRAM for
that has the results. So the memory we have is special purpose, right? If you're doing an aggregation, it's a stateful operation.
Yes.
Right? Then we copy it to DRAM once.
Yes.
But that's in native memory format, so it's in Arrow, for example.
Yes.
If your query engine understands Arrow, there's no copy within DRAM beyond that initial copy.
Right.
That's right. Any more? Any more questions? All right, so I'm around, others are around from NeuroBlade. If you have a question, come talk to us.